So good morning, everybody. So you can see that I have just a little bit defined better the title. So the topic is exactly the same, no worries. So I'm going to talk about, in particular, creating databases. So as a starting point to have data, and then what we can do once we have data. To do calculations, to replace calculations using machine learning or to accelerate calculations. And at the end of this lecture, I have prepared, so I have taken with me a little exercise of materials informatics that was given for the first time this last winter to the students of our Master of Materials Modeling and Simulations. And you will see it's really a very, very easy exercise where you can see how to get data, filter data, and then use data for a simple machine learning exercise. But we will get there afterwards. So first, a little bit basic information that you will need. So why do we do that, first of all? So why do we apply these different methods, combine them, use databases? The idea is to find new materials, so one possible idea, or to improve existing material, to optimize existing materials. And so here I've shown an example of a possible technology. This is something that everybody has. We have it in our pockets. But do you know how many different materials? Then here it becomes complicated because first of all, I will talk only about crystalline materials most of the time. So do you know how many different elements are inside a smartphone? And I always start the lecture with this question because the students sometimes have funny answers. So who wants to give a number? 40. 40, it's a number. More or less? More? Okay, another number then? It's closer, okay. 51, okay. So there are at least 70. So actually the most common, they are not just in very small traces, are about 40. So the number 40 was good. But so I found some nice web pages that I'll present, or some posters with information. So actually at least 70. And if now, we consider that in the periodic table there is not much more choice than that. So basically everything is already inside a mobile phone. But of course, this doesn't mean that we already know all the materials that exist, or that we cannot still optimize those that are already known. And so the idea is still to explore all the possible materials and try to find those that are more suitable for a certain application. For example, we would like to have better materials for solar cells. So in particular, when the topic is energy, producing energy or storing energy, still there would be the need to get improved materials. So, and of course, when we come to thinking about the problem of energy, or of making devices that use less energy, so in this way to save energy, very often we need one single material is not going to be enough, because the functionality very often is in the combination of different materials, what happens at the interfaces. So we will have at a certain point, if we really want to do something to solve the energy problem, to move from looking for single materials with certain functional properties, to look to combination of materials that can give functional properties at their interface. So just keep it in mind, and at the end I will say something more about interfaces. But okay, the databases that we have at the moment, they are mainly single materials, and so we want to predict new interface property or materials properties. So we need to try to make new materials and see which electronic properties they are going to have. And the periodic table is here, so there are not so many possible elements, but if we start to combine them to make binary, ternary, quaternary compounds with different stoichiometries, different crystal structures, you see that the number of possibilities explodes very, very quickly. So just the brute force approach, let's do calculations, for example, with DFT for everything is not going to work. We have to find some smarter approaches. And while we deal with the periodic table, we should also consider that we have all these chemical elements, but they are not all equal in the sense that some of them are polluting, some of them are toxic, some of them are very rare. So if we can, while we try to optimize and find new material, we have to think if we want really that this material is used everywhere as at the basis of a new technology, it cannot be one of these rare elements or endangered elements. So we should try to favor the chemical elements that are more abundant and that are environmental friendly. And so this is a poster that was in many universities I think in the 70s, and it's just a periodic table distorted in such a way that the area of each case is proportional with the abundance, the relative abundance of a specific chemical element. So you see that there are very big differences between the different chemical elements. And now there is an equivalent or new version of this periodic table with more information actually that is available on the webpage of the European Chemical Society. It's also updated, and there is also some text explaining why the different colors. And beside this different size of the cases, you can also see this color scheme, and you see here the legend, what the different colors mean. And you also see which chemical elements are particularly abundant, for example, in the mobile phone, in the smartphone. And so there are some things that are surprising, that I'm still, that I wouldn't have expected. Okay, then there is the carbon. You see here is 3 colors because, okay, it's, of course, there is plenty of supply. This is not the problem. But there is the problem of CO2 emission. So that's why I think it is considered a threat. And then, so there is anyways also the mines of diamonds and things. So it's considered to be anyway problematic also for political reasons. So it is a triple color, but everything is explained in the periodic, in this web page. And actually, so another thing, these rare earths, in the end, they are not so rare as one would think. So the big problem is just this prosium, and the other ones are all green. So, okay, so this is something that we should always keep in mind. And of course, we can include this constraint in our simulations and when we filter the data. So I've come to the outline, and I will just give you a little overview of theory, algorithms, and things that we use. But of course, this is has to be very fast. So if you then have questions or particular question, we can discuss about that also after the lecture. And then I will just focus on how we built the database. So the database Alexandria, that is actually the database that the group of my husband, Miguel Marques at Rural University Bochum, and my group members, so that we all contributed with calculations, but I have to say that probably 80% or 90% of the calculations have been done by my husband himself. So at home, he always sending calculations all the time, filling the cluster in Bochum all the time. And the database, of course, is something that keeps growing. So we started building it 10 years ago, or a little bit more. But every day there are new calculations that are included, and I will explain you what is then the strategy also there. And then I will tell you what we can do with the data as an example. And the example that I take is showing you how to represent the data, how to interpret the data that we have on the convex hull, so what are considered the stable materials on the convex hull of Alexandria, using an embedding. So I'll tell you then exactly what it is that we have made. And then I will tell you something about interfaces, because the next step is to go in direction to create a database for interfaces. It's a little bit more complicated, and I will tell you something. Okay, so and at any time you can interrupt me. and ask questions, or at the end there will be time, of course, for questions. So we want to design new materials. So first of all, we want to collect all the information on the materials that we know. And to do that, of course, it would be nice to have experimental data on every material property, all the materials that are known, but there is very little in literature, so we have to rely mainly on calculations. And now calculations can be done automatically using density functional theory. It's efficient enough, accurate enough, a good compromise to be able to create these large material databases. And also computers available. So in the last year, there has been a lot of progress in bringing together all powerful computers, already data available in material databases, new so efficient codes. And so this makes possible now that we have all these material databases. And the Alexandria and many other material databases are based on density functional theory. So the theory itself is old, but it is used more and more, so keeps growing the community, I would say, used in different fields, not only in, now I'm talking about solid state physics if you want, but it's used in many other fields of science. So this is the equation that one has to solve. And it's a very rather simple equation, so that's the power of the theory. Now, what has to be then the main approximation is what one, so there are many different choices for this exchange correlation functional. And depending on what one wants to do, there are functionals that are better than others. This is, of course, the topic of another lecture. But in material databases, very often the choice is to have to use always the same functional, because one wants, of course, to be able to compare the numbers for different materials. And so I will tell you then that what are the choices that are, for example, done for Alexandria that uses more than one exchange correlation function. So then, of course, if we want to predict new materials, it's not that we already know what is their crystal structure. So we choose some elements and we want to see, will they give something stable, thermodynamically stable, and in which crystal structure. So we need to combine also some technique of structure prediction. And this means that we have to consider, so if we have a certain number of atoms in the unit cell, we will have to consider possible position for these different atoms. This defines this Born-Oppenheimer surface, and moving the atoms, we try to get to the minimum of this Born-Oppenheimer surface. Of course, this surface doesn't have, it's not something very smooth with a single minimum. Okay, here you have to imagine this kind of object, but in many more dimensions. And there will be many local minima where you can get easily trapped in. So to find the global minimum is not always easy. And in any case, you may also be interested in finding other minima that are not exactly the lowest minimum, because we know that there are materials that exist in different polytypes. So in many cases, we can also stabilize phases that are not exactly the ground state for a certain composition. So the number of minima increases exponentially with the number of atoms in the unit cell. So this problem becomes complicated, but fortunately, there are algorithms of global structure prediction. There are several different methods that are rather established and that allow to find this minima. We very often use the minima hopping method, whose references are given here. In particular, we use it when dealing with interfaces, using a constrained search with the minima hopping method that is presented in this article. At the beginning, we were doing DFT calculations always, so with this minima hopping, that is just combine some structural relaxation steps with some molecular dynamic steps, with also some Monte Carlo way of choosing, accepting, or rejecting moves. And in the end, one should efficiently, if the simulation is long enough, get to the global minimum. There is never a guarantee, but in many cases, when we compare with the experiment, we see that we get to the global minimum. Of course, the DFT is very expensive because it's a lot of simulation, a lot of calculations of energy and forces. And so the first thing that we did, it was to move to density functional type binding to calculate energy and forces, because when it's really accurate energy and forces, otherwise you would get completely wrong minima that, or fake minima that don't really exist. And the next step, now we moved to machine learning force fields to do that, and I know that there are other lectures that will deal with this topic, so I'm not going to talk about machine learning force fields, but this is really very, very important because now with the universal machine learning force field, so for all elements of the periodic table, we can just do structure prediction much more efficient way than before, and this is super important when we deal with interfaces because we don't know what happened, what is the configuration at the interface changes a lot the electronic properties then of the material. Okay, so when we have different crystal structures, so we kind of put together some chemical elements, find what are the lowest energy crystalline configuration. And now this doesn't mean that this material is going to exist because, or at least the fact that it's thermodynamically stable maybe will also not tell us how to make it, but at least we can calculate if it will want this material to decompose in other compounds, or if it will like to be really a compound in that crystal structure. To do that, we have to put it on the convex hull, so to compare its energy with the formation energy of other compounds with the that contain the same chemical elements. And I show here an example in 2D, so this is easy to see. When we go to higher dimension, it becomes, of course, harder. So we have chlorine and tin in their most stable form, and here, of course, we are at 0 Kelvin, so we are looking at crystalline forms of this chemical element at 0 Kelvin, and similar thing can be built then if we include temperature, pressure, making instead of the formation energy, the Gibbs free energy. But okay, here we are at 0 Kelvin, and you see that there are this green line is the convex hull, and it connects the stable, so the lowest formation energy structures, in this case, tin chlorine 4 and tin chlorine 2. And then you see from structure prediction, for example, we get this tin chlorine in a certain crystal structure. We actually can have more points here with the different phases that have so different crystal structure with different energies. And this, we can say this is not stable. But we can say even more. We can measure how unstable it is, measuring this distance to the convex hull, that is this energy distance highlighted here by this arrow. So the larger this E hull is, so the distance to the convex hull, the more unstable the system is. So this will want to decompose in tin and tin chlorine too, for example. If we are closer to the convex hull, we may think that, okay, first of all, our calculations have errors because these are DFT calculations. So we know that our formation energies have errors, and in particular, so if the two extreme elements are similar, or so if you have a similar chemistry, very likely, okay, the error that when we do energy differences will be smaller than the error of the single energies that we calculate. But in other cases, we know that the error will be big. So, okay, the closer we are, the more likely it is that, okay, maybe there was an error, or that the system can be stabilized once that we put in temperature, pressure, we can play with these parameters, or that may be some defects that kind of stabilize a certain phase. So there are many things, but if we are too high, too far from the convex hull, then it's super hard to have something that is really stable. And we can see it comparing our theoretical convex hull with the experimental convex hull. And then, of course, there may be some other phases that we simply haven't calculated. So the convex hull, theoretical convex hull, can be not complete. So we may be saying this is stable, but in reality, there is another phase that is still lower in energy. So the convex hull is an evolving object. It's not just fixed there. Here the same convex hull, so this line chlorine tin is here, so along this side of the triangle, but here we have a ternary phase diagram now, and you see we added the rubidium, and this is because this is, here we have some perovskites in the middle, and the color scheme now will tell you the formation energy, so you see now that these lines are the convex hull, or are the lines that would be equivalent to these lines here, but it becomes harder to represent this object in 3 dimensions. Still it works, so we can make these nice plots, but if we go to higher dimensions, it becomes very difficult. Still, we can do it, so we can calculate, obviously, the convex hull. We can calculate the universal convex hull with all the chemical elements, and I will show you that we do it for our database Alexandria. So on the Alexandria database, we have now about 250,000 compounds on the convex hull. Yeah, so we will enter afterwards, but of course then we need some smarter ways to represent things, because we cannot see directly these nice lines and say, okay, these are the stable compounds. So if we want to interpret and understand something of the global convex hull, we need some other way to represent things. And yeah, so I told you something about doing calculations with DFT, what kind of calculations we need to do to build the Alexandria database. But now you see, so we are, so this figure comes from a review articles of some years ago, and it shows the different paradigm of science, and you see that we are now, we went from the 3rd to the 4th one, and everything, so let's say that now it's really hard to work without data and without machine learning. And you can also see it from this plot that is already outdated, because it runs until 2020. I should update it, but I'm a little bit afraid what's going to happen updating it. So you can clearly see that the growth of machine learning is very, very fast. Actually, it's really starting from about 10 years ago that things really started to speed up. And even if density functional theory is also a growing theory, so here it's just measuring citations in articles that have, in the abstract, I think the word either machine learning or density functional theory, title or abstract. And you see that DFT is still growing, but that machine learning is growing much faster, and now surely has got much higher. And so there was, in 2014, in this article with the 100 most cited papers, and there were 13 that were related to DFT, also some technical aspects of DFT. But now there is a new one that just came out, and I still didn't have, but I saw it just a couple of days ago in the archive. And the new one doesn't have any DFT anymore. It's basically everything is about machine learning. So this also shows that machine learning is really an emerging topic. And okay, this was also recognized the last autumn with the Nobel Prizes for physics and chemistry. So, and you also, well, the students I think have already understood that. So also in our groups, most of the students want to work on topics related to machine learning, and yeah, so this is kind of the future. Okay, so but there are great already algorithm models, but still, if we don't have data, this is totally useless. So I was last week or 2 weeks ago at a conference on AI for materials. And there was a very nice talk by Christine Persson, who is leading the materials project. And she had a very nice first slide in which she said that the students wanted to work in machine learning. And so she had a beautiful picture of a Ferrari. And then she was telling them, you don't go anywhere without fuel, and the fuel are the data. So without data, there is very little that one can do. And in many cases, we have very small data sets. If you just rely on experiments, it's getting better. So there are more and more high throughput experiments, and there are data sets coming from experiments. Or if, for example, if we have very accurate calculations, we will also have small data sets. And then in that case, one cannot do much. So one can use simple machine learning models. So in the exercise, that we will look later, we just use some decision trees, some simple algorithm, because, okay, to make quick exercise, we are not going to use too much data. So this can still be useful. So for example, if we do machine learning on top of DFT calculations and we want to correct to more accurate calculations, sometimes one doesn't need to have so much data or so complicated models. When one has a medium data size, then one can do a little bit more complex thing. So for example, to pre-filter things, to do more accurate DFT calculation for a smaller set of systems that can be more interesting, or training of machine learning force fields, one can also build new DFT functionals from the data. So there are many examples of this kind of calculations. And then when one has a really larger data set, more than 1 million data point minimum, so one then can really try to bypass completely, directly predict things, let's say, without doing any calculation, not only to accelerate calculations. In that case, one can use more complex machine learning models. And so ideally, one would like just to predict materials property without having to do any additional calculations. But okay, it's still maybe a little bit, still not there. And we'll say something about that maybe at the end of the further developments. Okay, so said that the data is really important. So without data, we cannot do any machine learning modeling. And so I will want to tell you something about the Alexandria database, a little bit how we built the database. And so it started with high throughput calculations, kind of 10 years ago, for a subset of or families of materials. And the first one that we addressed, as we were interested in material for energies, were perovskites. In general, perovskites are a fascinating class of material because there are really a lot of different properties in changing the composition. One can get the materials with very different properties. And so what we did some years ago, and I want to show you this example because it's also a nice example of interaction with experiments. So we started with this ABX3. So this is the cubic perovskite, the smallest possible unit cell that you see here. But then, of course, there are still many perovskites in the database that have multiple of this 5-atom cell and are kind of distorted. And we still say it's a perovskite as long as we have this network of octahedra. So this octahedra, for example, with oxygen here at the vertices of the octahedra, are typical of the perovskite structure, can get a little bit distorted, but if we still keep this 3D network, they will be still perovskites. And now we looked, we noticed that, okay, there were perovskites with these elements, so these anions creating octahedra. There are also inverted perovskites where you have cations on actually most of the stable perovskites are inverted. But we were looking at these classical perovskites and we asked ourselves, is it possible to have a nitride perovskite, so with 3 nitrogens, so A, B, and 3. And of course, so when we move from oxygen to nitrogen, we go on the left in the periodic table. So it's as the cations should compensate to have a compensated compound, the oxidation state of nitrogen. This is not so easy. But, and we didn't know at the time, we had never found these articles, but then we found afterwards. So in the 95, there is an experimental article that reports a nitride perovskite with thorium and tantalum. So, and actually at the time we were not including, so thorium was not in our set, so we didn't have lanthanides and actinides in our set. And so you see that then we tried. So we looked at the stability. So we did fix the cubic perovskite and try to change all the chemical elements. So we all possible combinations. There were not so many anyway, because we have A and B here on this side here of our graph. So here, this is kind of a one-dimensional representation of the periodic table, but it's not done in such a way that we just order them by atomic number. We order them according to what is called the Pettiford scale that will come again later. So it's a one-dimensional representation of the periodic table where chemically similar elements are close one to the other. And so that's why, if you look here, we see a region of green. So this wouldn't be a cluster, it would be just some isolated green spots if we just had ordered the chemical element A and B using the atomic number. So this is in milli-electron volts per atom, so there's not the scale here. And so you see that there is negative. So what does it mean if the distance to the convex hull is negative? It means that we find something that was not in the database, and it is lower than the existing convex hull. So after we have to recalculate the convex hull, and this will shift everything down, so we will not have any more negative formation energies. But for when you do the search, you find some things that are negative, so it means that they should be on top of your convex hull. And here there is this cluster. So if you look more in detail, we did then the structure prediction. We allowed to have larger supercell, and we saw that some of these green things there were not remaining in the crystal structure of perovskite. Some were getting just some distorted perovskites, but some were just breaking the octahedra and getting to some monoclinic crystal structures. So those are still compounds that we have to add to the hull, but they will not be perovskites, very likely, because there are some phases that are lower in energy that destroy the octahedra. And then here, okay, this is milli-electron volts per atom. So this is also a mistake, I think, in the paper. So this is a periodic table now for fixing lanthanum in the position, chemical composition A, for the element A. And then we have X that goes through the whole periodic table. And with this color, you see what would be a stable compound and what not. So it's, again, the distance to the convex hull. And what is red is unstable, so most of these things we can forget them. But there are green things, so with lanthanum, and in particular molybdenum, tungsten, and rhenium are still perovskites, and yeah, so they maintain a perovskite crystal structure. So at the end of the 21 stable A, B, and 3 phases that we found, 3 remained perovskites, but they contain lanthanum, and so then we could get a step further and replace lanthanum with lanthanides and then analyze the whole family, because yeah, they were still stable also with the lanthanide. But originally we found these 3. And so this was published in 2015. So in 2019, we published then a characterization of all the lanthanides and look at their magnetic properties. And in 2021, this article appeared in Science, and it was very much advertised. And it comes from NRL in the group of Tsukutayev. So they synthesized the lanthanum, tungsten, and 3 perovskite. And they tested, they made some nice crystals, and they tested the properties. And so we had predicted that this was going to be an excellent piezoelectric material. And indeed, that was also found in the experiment. So this was nice. And actually, so it's not so rare. So I also found a review article in which was showing a prediction that were then confirmed. and there is a trend. So of course it takes some time to make things, especially so in this case it's very hard to make a purely nitrogen perovskite because the oxynitride perovskites are also very stable. And so if some oxygen gets in, one would get an oxygen nitride perovskite and not a purely nitrogen perovskite. But it's possible to do it. So this was a confirmation. And then more recently, other things appeared. Maybe go back here. So the lanthanide perovskite. So we both with tungsten and rhenium. So the lanthanum, tungsten, and also the one with rhenium, they were made. So this one, lanthanum, rhenium, nitrogen 3, it was made, I think, in 22. And the lanthanides, we saw that many of them had a tendency to distort and to break the perovskite structure, but not all of them. And we look at magnetic phases. We didn't look in detail to antiferromagnetic phases because the size of the simulation was getting very large. Still, we predicted that some of these perovskites could have interesting magnetic, so ferromagnetic properties with high saturation magnetization and also high anisotropic energy. Maybe not so high Curie temperatures, but still we thought it was interesting to look at this composition. And some of them were very recently made, also some in 2024. But some of them are then more stable in antiferromagnetic phases rather than ferromagnetic phases. And they stay, so for example, this gadolinium, we had it ferromagnetic, so paramagnetic, it was basically with the very small ferroelectricity, with in the monoclinic phase, but it's experimentally found that it can be stabilized in an antiferromagnetic perovskite phase. So there is still work going on in this perovskite. This is just one example, because of course, when we do high throughput calculations, we predict a lot of different phases. Sometimes experimentalists find something that can be interesting and make it. But okay, this was an example, and it was very limited. So we had started with 4,000 different compositions to look to some, at the end, get 3 stable perovskites. But this was also maybe easier to transfer the information to experimentalists, because at the end we tell them, look, we have 3 interesting perovskites, can you try to make them? Sometimes it's harder because we put a lot of things inside, we get 10,000 new stable materials, and then it's a little bit more difficult to see what could be then interesting. Then one need also to have some tools to interpret a little bit more the data. So we went on putting different chemical elements inside and looking always, for example, if we are interested in material for photovoltaics, we have to decide some filters to select materials that would be good for a specific application. So one thing that we did in the past, it was to look first what could be stable, and then look at the size of the band gap to filter out some materials with interesting band gap, let's say for photovoltaics, or if we wanted transparent conductors, we were looking to larger band gap, so it depends. And then we were looking also at effective masses to have anyway good transport properties for electrons and holes. And so we went on with this ABX3 perovskites, this time also changing the chemical element here in the position X, still putting anions here at the beginning, here these gray elements. And we got new perovskites, and then we analyzed always the properties, some selected properties. So there are always big tables in these articles and some plots. So for example, we are looking at the band gap and looking some specific size of direct and indirect band gap. So usually then when we do calculations with structure prediction, we use some functionals that are, let's say, low quality functionals, like this PBE functional that is used also in the materials project database. But it's usually enough to calculate energy forces and build our convex hull, and the calculation are fast enough. But then when we look at the band gap, for example, this is not good enough. So for the band gap, we do, for example, calculation with hybrid functionals that will give us reliable band gaps in the region of interest for semiconducting materials. Here we calculated also the ferroelectric polarization, and here you see this lanthanum tungsten N3 that has a very good piezoelectric ferroelectric properties. And then we included molecules, so we did also these perovskites with little molecules. We included different small molecules that could fit in the crystal structure, and also looked at the two-dimensional perovskites. So when we break this network, 3D network of octahedra, but still there are layered perovskites. So, and all these runs brought a lot of new, promising, interesting materials. So we were then filtering the properties, in particular, again, gap and effective masses, to look for some materials that could be more interesting, more stable, maybe of the hybrid perovskites used for photovoltaics, but keeping the good band gap and the good transport properties. And actually, it was, in conclusion, it was it's not so easy to stabilize. And I mean, the solutions that we have with lead are probably still the best that are available. But yeah, so looked at the whole and also at electron effective masses, and always screen out systems with, for example, small effective masses that could be more interesting for further than more accurate studies. So every time, so each one of the study led to some conclusions on this specific class of materials, and at the same time to new data that could be added to the database, and all this contributed to building the database. And so you see, for example, in this case, with this methylammonium lead iodide, we found interesting substitution for methylammonium could stabilize a little bit the structure. But we also found that the best way to go is probably to replace partially, so to do some alloying, replace only partially lead, because getting rid of lead was anyway creating problem either to the band gap or to the stability of the compound. So these were things, and now I will just kind of skip the rest. So I have some other slides showing other families, so enlarging. So we looked at quaternary compounds, always with perovskite structures. So these are called double perovskites. And we looked at alloying for perovskites and so on. And this brought many, many, many more compounds. And actually, the first applications of machine learning, we made it only on perovskite subset of the database, because we had so many data on that. But I will just skip this. Okay, so these are just examples of how the database was built. And at a certain point, so we realized, okay, we already have a lot of data. Still, it's a little bit biased, our data, because we have a lot of perovskites. We had a lot of other families that we had looked with particular interest, because we were thinking, okay, they may have some promising property for this application. But we wanted then to make the database more general, or as general as possible, and as large as possible. And so the idea is to really get the theoretical convex hull of all materials. So at a certain point, so this convex hull has to be finite in some way. So we have to be able to define all the compounds, crystalline compounds that are on the convex hull. And so this is what we did at the first. So it was to just look at what is existing in nature. And try to translate it to our database. So introducing this concept of chemical similarity that is then at the basis of our embedding that I'm going to present in a few minutes. So that's why I tell you more about this concept of chemical similarity. So if you look at the experimental database, there are some compounds that are there because they are stable, they are made. And then you can compare and see that, for example, there are two crystal structures that are equal. Two compounds that are equal, have the same crystal structure, and have just one chemical element that is replaced by another one. So if we find one of such pairs, then we can say that these two chemical elements are similar, let's say. So we will give them some high similarity index. So we have to build then a measure of this similarity. And so this was done by building a big matrix, in which symmetric matrix, in which on the it will have the size of the number of chemical elements that we have in the Alexandria database, that is 89. So there are 89 chemical elements. So we'll have this 89 times 89 matrix, and every time that two chemical elements can be in the same crystal structure, just replacing one the other, then we will put a 1, so in this on the off diagonal of this matrix. So if it happens in more different crystal structures, we will have higher numbers there. So how many times this happens will stay on the off diagonal elements of this matrix. And on the diagonal elements of the matrix, we put how many times these chemical elements appears in different crystalline crystal structure. So building this matrix and then normalizing the rows of this matrix, we get a measure of, so we'll have a probability that one chemical element can replace another one in a certain crystal structure. And then, guided by this measure of similarity, we just made substitutions, so not random substitutions, but targeted substitutions. And then went to check, is this new thing that we get already in the database? If not, is it stable? And in this way, we obtained a success rate of 10%, that is much larger than what one gets by random substitution. And actually, in many cases, similar to the success rate of machine learning when you want to get a new compounds. So using data that was already in the experimental database. And so you see how the things go. You start from one composition, you see what are the most likely substitutions, you see stable, unstable, and do different rounds. So we made in total 3 iterations. We got a substantial increase of the convex hull of Alexandria. At the time, it was not called Alexandria yet. And then using that database, we already at the time it was about 2 million compounds in Alexandria. We made a first application using a crystal graph neural network. So the data was coming from our database, the Materials Project, Auflolib. So we were compatible with these databases. We're using the same code, the VASP, to create the database, and the same exchange correlation functional PBE, and same parameters for convergence. So this was all compatible. So we could put all the data together. And at the end, we ended up with this first database that was large enough to do some machine learning using a little bit more complex architecture. So we use the crystal graph to represent a crystalline compound. So this was already published some year before this suggestion. But what we did, it was not to use information on the lattice parameters. So we were introducing a certain prototype, so it's certain defined symmetry coordination for our crystal structure, but we were not necessarily knowing what was the lattice constants, because otherwise we should relax the structure with some, for example, machine learning force fields or DFT to get the crystal structure. We didn't want to do that. And so we were giving information to the nodes, information on the elemental chemical species, and the edges of the graph contain embeddings of the distance between, or coordination between the atoms. So we were doing it up to a third order of neighbors, but without giving the exact bond length, exact distances. And with this network was using then already attention mechanism and message passing. So it is already a lot of parameters in the network. So this was possible to train only because we had enough data. So we had tried before and it was simply not working. And but you still see 60 million parameters, mainly in these message passing steps. it's still much, much less than what would be a natural language model like ChatGPT-3, that we know how many parameters were there. For the ChatGPT-4, we don't know exactly. So it's still much, much, much more. But this network still was relatively good to predict stability. And in particular, it was also able to distinguish between different forms, so different minima of this potential energy surface, because if we had the two phases that were input in the network, it was able to order them correctly. So here the correct ordering of different phases. If the energy difference between these two phases is 0.1 electron volts, was basically 100%. Of course, if they are very close, the two polymorphs in energy, then the success rate is lower, but still it was quite high. So we were very satisfied with this, and also with the error that we found in the prediction of the energy, or formation energy, or energy distance to the convex hull. But still, we noticed that our database was still very biased. So if we were getting some crystal structure that were very different, or that was not so represented in the database, or some chemical elements like lanthanides or actinides that were not so much represented, immediately the error was getting larger. And so that's why we worked a lot to improve the size of and the quality of the data in the database. So trying to make it unbiased as much as possible, adding data on chemical compositions that were not enough represented, or adding crystal structures that were not represented. And so this shows us kind of some histograms of the database in different phases of the growth of the database. And what we have now is Alexandria, so you can access the database just with the QR code, or you just write materials database Alexandria at RUB, so Ruhr University Bochum, and you will get there. So the database is open, so it's fair data. You can do whatever you want with the data there. So there are DFT calculations with VASP. For now, it's more than 5 million compounds, but okay, this is the order of magnitude. Not only PB calculations are available, so PB functional is the one that is used in most materials databases, but we have also PB sol calculations, so it's a version of the PB functional, still a GGA functional, but that gives better geometry for solids, so we already tested that. The geometry are very, very accurate, and so for many applications it's better to use PB sol than PBE. There are also scan calculations, because the scan functional proposed some years ago was supposed to give much better formation energies. So we are not sure that it really gives much better formation energies after benchmarking everything, but okay. So the idea is to try now to get even more accurate functionals, even more expensive calculations. So for example, with hybrid functionals, slowly should be able to replace the PBE calculation. Of course, it takes time, because meanwhile the database grows with new materials, so it takes time. There is an optimized interface. So in the tutorial, I'll show later also, there is something about this. There are, the format of the files is JSON files. If you just want to have all the input-output files with which calculations of Alexandria have been done, this is available now in Nomad. So this is very recent, so we transferred the files very recently. Of course, it's an enormous amount of data, but you have everything available now in Nomad database. Yeah, I think I said, and there are there is also some sub-databases, so there are 3D crystalline materials, but also there is a database now of 2D materials, and smaller, but kind of nanowires materials. So also this can be useful for specific applications. So everything is included in the database Alexandria. And now if you compare Alexandria with the GNOME convex hull, so this was the Google article appeared in 2023, in which they proposed their own convex hull with 400,000 stable compounds. Unfortunately, the data from which this convex hull is calculated is not available. So, and even the convex hull, so you have the list of this, so these 400,000 materials, you know which they are, whatever, but you cannot really use this data. It has a strange license, so in the end it's kind of useless. So you know that Google, with a lot of computational power, could made enough calculation to obtain a convex hull with 400,000 compounds. Now Alexandria has more than 200,000. I think that last week it was almost reaching 250,000. And yeah, so if you compare with the experimental database, if you remove alloys and compounds that are not fully defined or whatever, so there are many less stable compound in the experimental database. So this is the order of magnitude, and well, I think that likely this is the materials that one can get, right? I don't expect that there are millions of materials, so probably this 500,000 is the number of crystalline material that one can get in the end, finishing all calculations. But this is the target still to reach. And so if you look at the distribution of material properties in Alessandria, this is also very interesting. So one can make very nice plots. So we have 5 million compounds. And so, for example, most of these compounds are unstable. So you see that when you look at the hull distances, so most of them are unstable. So most of this distribution are very asymmetric. And so usually the more asymmetric the distribution is, then the harder it is to train some machine learning models. So the distributions that are not so far from normal distributions are usually much easier to deal with. But okay, it's not what nature likes. So you can see, for example, here also the gap. So we have most of the materials are metals, and then we have a distribution, okay, of gap that decreases. And yeah, so also this makes that, for example, we need, it's very hard to predict accurate gap unless you do it on a subset. So like I consider only semiconductors and then I look at the gaps. But if you just put together metals and semiconductors, of course there are many more metals, and the things becomes complicated. So, but all these things can be then tested doing some machine learning with existing machine learning models, like this CrabNet that we use a lot for testing purposes on Alexandria database. And so if you can see, for example, how the different properties that have very different distributions will be easy or very hard to train. So increasing the size of the training set, you should always get a smaller error in your prediction. But there are some properties, like here, as I told you, the band gap, if you consider both metals and non-metals, it is very hard to train to get to a lower error. Or also the magnetization is a property that is particularly hard to train. But other quantities like the crystal structure, if you want the volume of the unit cell or the total energies, formation energy, those are rather easy to train in a precise way. And then, of course, when you have a machine working, you can do transfer learning. So if you have a lot of data with a certain functional or for a certain property, then you can try to use the same machine and keep training to get some other property or a property with a higher accuracy. So we did several tests, and yeah, so in some cases it works, this transfer, in some other cases it doesn't. So when you try, for example, to calculate the same property, just changing functional. So we had a large database of PBE calculations, smaller database of scan calculations, try to do transfer learning. So this works, but if you try to do it with two very different properties, as it should also be, okay, makes sense. A machine that predicted very well a PBE volume will not necessarily predict well formation energy. Yeah, unless you kind of have to retrain it. So it will take a lot of data to train it again. So the transfer in this case doesn't really work. Okay, now I wanted just to show you how to use embeddings, because this is the part then of our homework. And I will show you some example of things that we have done. So here I will present our own embedding, this Pettifor embedding that we have recently submitted for publication, and that is available, the embedding. So here, at this address here, and I will of course share then all my slides after the lecture. You can get some examples, so an example notebook to use the Pettifor embedding. I will show comparison with other existing embedding, and in the homework there is another typical, so I think it was Magpie that is used, but yeah, then you can change from one to the other, compare and see how they perform. So the idea is that how do we represent a crystalline compound? So we need to represent the crystal structure and the chemical composition, and we want to do it in a way that is efficient to be used in machine learning, so it can be given as an input to machine learning, that at the same time also something that is for us easy to understand, because the problem of machine learning in many cases is that yeah, so we lose a little bit our grasp on the things. It's much easier to solve an equation, you know what you are doing, you know what you get, it's easy to interpret what you are getting. But when the machine predicts something and you don't know exactly why, then you feel a little bit bad about that. So our idea was to have at the same time a representation of the crystalline compound that was good for our interpretation, and that was also useful to be used directly as input in machine learning applications. And the idea is the following, is to use again this concept of chemical similarity I have talked about before. So we have this scale of similarity. So if two chemical elements are very similar, so their similarity index will be dissimilar, sorry, the similarity index will be 0. If they are very similar, it will get close to 1. And so we say, okay, then we start from a simple one-hot representation for the chemical composition. So it means that we have, okay, here we have 3 chemical elements, but we have to imagine our 89-dimensional chemical space. And if we have, for example, here rubidium to oxygen, okay, we will move 2 steps on the axis of rubidium and 1 step on the axis of oxygen, and the other coordinates will be 0 for all other chemical elements. Then this vector is renormalized in such a way that all vectors of composition lie on the sphere with the unit sphere. The same thing, we can do it with our fingerprint. The difference is that the cosinus of the angle between 2 axes is equal to this similarity index. So if the chemical elements are very similar, have a chemical index that is similarity index close to 1, the axes will get closer. And so the distance then between 2 chemical compounds, can be closer if they are similar, and on the other end, they will be more distant if this angle is close to 90 degrees, so if the 2 elements are distant one to the other. So if you understand, it's just still a one-hot representation if you want, but the system of axes is no more Cartesian, is no more orthogonal, in such a way that the closer compounds are more chemically similar. So we also define this way a distance. And I show you now how this can be applied to a simple example. Okay, I wanted an example where we don't have now a different chemical crystal structure, sorry, just looking at this description of the chemical composition. And so I just consider elements, chemical elements, and I want to do a 2D map of these chemical elements using dimensionality reduction techniques. So what it means that now this representation that I have here, it has 89 dimensions. And it's something that, okay, it would be nice to plot the chemical elements here inside and look at their distance. But in 89 dimension is very hard to make, but we can use this manifold learning and do reduction and go to a two-dimensional map. It's like making from the Earth three-dimensional to a two-dimensional map, trying to conserve as much as possible the distances. And so this is a 2D map that we obtain with UMAP. It's one of these techniques for reducing the dimensions. And you see that the fact that our Petty-4 embedding keeps closer chemical elements that are similar allows kind of to recreate groups of the periodic table in this 2D map. So this is a data mined representation of the periodic table, because the chemical similarity comes from experimental database, data mining and experimental database. So it makes sense that as the chemical similarity comes from the fact that the chemical elements are similar, in many cases are in the same column or whatever, this then is reflected in this periodic table. If we do it instead using this one-hot encoding with the orthogonal axis, this is the result. So here there was no chemical similarity and there is nothing visible out. So we then don't get any clustering of chemically similar elements. This is what we obtain with Mat2Vec. So Mat2Vec is another embedding. It's a literature word embedding. So the embedding was done with machine learning using literature, so scientific literature. So it contains also information that comes from experimental data, if you want, but it's kind of a more indirect way. And you see, still, you can recognize some very well-defined group here. So, yeah, with what are these? These are lanthanides, but it's yeah. So here we have a noble. So some transition metals, but still, it's still not so clear so as it was in here in our Petty-4 with our Petty-4 embedding. So this is what one obtains with Magpie. So this is a human-made embedding containing elemental properties of the atom. So yeah, properties of the elements. Some different properties of the element that come in some way from the knowledge of the periodic table. And so you see that also in this case, you can see clearly some structure in here. So this Magpie is also what we are going to use then in the little examples in the tutorial that I will present soon. Yeah. So with our Petty-4 embedding, we define, so as I told you, this distance. So two similar compounds should be closer in this multidimensional space. And so we looked at these distances and we compare them also with other distances based on a non-Euclidean measurement of this, because in the end we still have this Cartesian space, even if not non-orthogonally, we are just measuring Euclidean distances. But there are other ways of measuring distances that were proposed, like this elemental mover distance, that it's based on this concept of Earth moving distance. And so this thing is, again, based on the same concept of chemical similarity. So it should be similar to what we have. And this is another one. The Sigrid distance is again an Earth mover distance. And it's also based in some way on some concept of chemical similarity, not the same chemical similarity that we have defined. So if you compare now, let's say, what is the closest chemical element to sulfur? Our Petty-4 embedding distance would say it's selenium, the closest, and then polonium and tellurium. And these Earth mover distances that were based also on similarity also give selenium. Then here we have oxygen and tellurium. Okay, oxygen is not very far, is kind of the next one that comes here. But the other gives some things that are less intuitive. So why gallium or why nitrogen? So this is a little bit harder to understand. Or silicon, most of the different choices will give us germanium as the closest. And our embedding says then comes tin and then gallium. And here for silver, for example, you see copper, gold, so we would expect that. Why, for example, germanium is weird, so to have it here. But okay, so this is what comes out. But in this way, we can try to understand a little bit better similarities of different chemical elements. And then now, what we did is to use it to look at the convex hull of Alexandria and try to understand or look at Alexandria database. So here I am getting this big family of perovskites. So these are just the 5 atom in the unit cell perovskites in the database. And you see many of them are red, so unstable. So there is already these colors. There is a lot of green inside, but it's kind of in the middle of the reds. And each one of these kind of islands is specific. So this is a zoom in this region here. We find a specific composition with a specific octahedra, so element forming the octahedra. And then usually this main island, there are transition metals, and then in the smaller island, there are other compounds, and then there are also some inverted perovskites. So it's easy to zoom in and look at the structure and to understand a little bit better. Unfortunately, this thing should be interactive. Otherwise, it's very, very hard to understand. We also look on Alexandria convex hull at different families of like perovskite, the laphosite, Hafhäusler compounds, and they create some groups or regions in this big atlas of material. Then we can also use this distance to say, okay, can we find a chemical, a compound that has similar electronic properties to, for example, silicon. And of course, we found germanium, diamond germanium, silicon carbide, but we also found something less intuitive, like this nickel silicon 3 phosphor 4, that has a band structure that is indeed quite similar to the one of silicon when we compare it, but it wouldn't have been so obvious to find. Okay, I think that I don't have time to talk about interfaces, but I will give you the slides. But then here the idea is really to make interfaces and start to have a database of band alignments at interfaces and electronic properties at interfaces to slowly build something that can be used with machine learning. But I think it's a little bit out of topic, so I would rather skip and get to the open problems and the conclusions. So I think that with this big material databases, we have now a lot of data to use for new prediction. There will be more and more data coming from high-throughput experiments, so that will be able to combine with theoretical data. And we also need to do calculations with better functional or more accurate methods to get more predictive power. And then, of course, an open problem is the concept of, okay, the fact that something is thermodynamically stable doesn't mean that it can be made experimentally. So there are some descriptors for synthesizability that are coming out, in particular from experiments, from experimental data, but there is still some work to do on that. And so probably the open challenges, we can still improve the databases of DFT calculations to include as many variety as possible. And we need better data, so we need more data now to be able to do things that are still not possible. And I think we are close to reaching the point where we can say we have reached the universal convex hull, at least from theoretical calculations. And then, of course, we will have to include temperature and maybe include alloys, so include things that we are for the moment just not considering in our databases. But there is still a lot of work, but still there are also many progress steps. And I would like to thank here at the end all collaborators. So my group in Bochum and Miguel Marques in particular for all collaboration on machine learning and Alexandria database, and 2 of his group members that contributed a lot on the things I've shown, Antoine Leuve and Aishen Wang, and collaborators also Tiago Cerqueira in Coimbra and Jonathan Schmidt at ETHZ, and funding agencies. And here I just leave you with the QR codes of Alexandria and the Petitfort embedding. And yeah, if you wanted to use it for any applications, of course, we are very, very happy to have more and more users. Thank you.